Okay, so now we're going to look at the Sawtooth waveforms using our oscilloscope here. So we are using the mbed board pin 18 to give you the Sawtooth waveform. So if you want to look at the oscilloscope, we must use the probe to connect the pin 18, which is the pin which gives you the analog out. Okay, then the ground connect to the negative of your probe. So these two have to connect to your, this is your ground of your probe, connect to the ground of mbed. Then this is the positive side, connect to the pin 18. Then you can see you'll see the sawtooth waveform in the scope as in. So this is how you see the this is how you program it. And if you look at the coding, they are just giving you analog out by increasing it every times by 0.1. So you can see it should be have a 10 step size. 5, 6, 7, 8, 9, 10. There's 10 steps in here. From 0 up to 1, they will stop. So this is how they do the coding. If you this is the times. 0.01 means the time for each step size. Okay, how far the two step size. Then the next one is the sine waveforms. So you can generate the sine waveform using this formula also, the sine waveforms. Then from here you can see this is the curve generated by your mbed analog output. We are using the same pin or using the probe pin 18 also. So if you look at the sine wave, this is a sine wave you are able generated. But if you look into it more closely, you can see basically there are also a step size. You can see the step size, right? So they are analog output to simulate out the sine wave, so you can see the step size. If you want it to be more curve, more nice curve, you can try. You can reduce the step changes and this time. Okay, so you increase the times, you are able to have a better curve. If you reduce the times, if you reduce the wait time to a smaller values, it will have a shorter step, which means the frequency of this sine curve will be increased. So if you want to have a better curve, you need to have a more close to sine wave, you need to have a smaller step size, which is the I plus have to be reduced. Then you have better curve. Okay. Then they use 0.5 is to reduce the sine wave to half. Then and they need to plus with 0.5 again, so that they will shift the whole curve to the positive side. Because if you the analog output, they are unable to give you the negative side of the waveform. So if you're using a simple just this sine formulas, then it cannot give you the negative value. So when you go to negative, the analog out will just give you zero voltage. So at the end, you'll see only half of this only. You'll see only half of this curve. The bottom one, it will become flat. Okay, we can try to change it to the without the 0.5. Then you can see what is the output. Okay, so as you see in the code, in the scope, this is the waveform for these formulas without the plus and minus, plus 0.5 times 0.5. So you can see it only have the positive side. Then the negative side will become flat, because the negative side is the analog cannot give you negative values. So that's why they will give you straight away a zero values only. So that's why you need to shift the curve to the positive side by adding the 0.5. Then the times the 0.5 to make it half values, only they add it up. So you'll get back 3.3 at the end. So this is how they do to display the sine wave in your oscilloscope using the analog out, because the analog out only able to give you the positive values. Remember your sine, it will go from 0 to 1, then 1 go down to -1, then only come back to 0, right? The sine waveform. So that's why I need to have a 0.5 plus with the sine waveform. So this is the waveforms where we reduce the step size to 0.005. So you can see the curve is more smooth. You don't see so much of a steps in that. But if you want to see that, you can try to zoom in, then you will also see the step size actually. They still should have the step, but it's very small until you cannot see with your eye. We try to increase the there is still some small step changes if you look at the scope. Right, if I try to zoom in here, you can see there's a still small step size. Right, this is still a staircase. This is we reduce the step size, so every time it reduce very short changes only, so you cannot see the sharp step. Right, we reduce the changes of voltage in every step if we change these values. So that's why you can see the changes is very small only. So at the end you cannot see it very clear. You have to zoom it very large, then you're able to see the step changes. Yeah, you can see that there's small step changes happen in the curve, right? So I've tried to zoom in, then you can see that this is the step changes. Okay, if we zoom out, then we will just see a very nice curve. So if we zoom out, then we just see a very nice. If we zoom in, you'll see the small step changes. So this is how you do getting a better curve. You need to reduce the step size. Okay, then there's a limit. The minimum voltage changes can be done is based on the resolutions of your analog out. So if your analog is only 10 bits, then the maximum resolution is only 3.3 volt divided by 1024. The minimum step size you can get. It depends on how many bits of your analog out can perform. Then this wait time is to define the step size timing difference. So if you increase this one, then this frequency will be reduced. If you reduce this one, the frequency will be increased. Means more curve at shorter time.